So what we're going to be talking about in this video is we're going to find some function that we can demonstrate is not computable. That is, there's going to be no Turing machine that can actually compute this function. Now, we certainly know already that some such functions do exist. We knew this basically since the first couple of weeks of class based on this counting argument, that we knew that there were an uncountably infinite number of functions, but there were a countably infinite number of possible machines that we could represent. So that must mean that since there's some functions without representations, there's some functions that aren't going to be computable by some machine. So what we're going to be doing here today is we're going to be identifying a specific function that is not computable. And this function is going to be this self-rejecting function, where basically we're going to be talking about this function that determines whether or not Turing machines are going to reject themselves. So we need to discuss a little bit of machinery before we can actually talk about this function. So the first thing that we're going to need to talk before we talk about the self-rejecting function is we need to have a way of representing a Turing machine as strings. So one of the things that we're going to want to do is we're actually going to want to be able to give a Turing machine as an input to another Turing machine. This might seem like a weird thing to do, but it's actually something you do all the time when you look at Python programs or any other kind of program. That it's very often the case that you have some programs that receive other programs as inputs. For instance, compilers do this. Every single time you compile a program, that's you handing one program as an input to a different program. So we're going to do sort of a similar thing with Turing machines here. We're going to have a Turing machine. We're going to be considering Turing machines that are going to be taking other Turing machines as input. So in order to give a Turing machine as an input to another one, we need to represent Turing machines as strings. So let's talk about how we can do that. So the first thing we're going to talk about is we're going to define this fancy m function. This fancy m function is essentially going to be taking a string as input and then returning some sort of machine, Turing machine, as output. So fancy m applied to w, if w is going to be a valid Turing machine according to our description of Turing machines, how we're going to be describing them with strings, then fancy m applied to w will give us that machine which w described. However, if there's something wrong with w, maybe there's a syntax error, something like that, then in that case we're going to be it's going to return this reject machine, which is basically a machine that doesn't do anything except halt and reject the input. So fancy m applied to some string w is either going to give us the machine which w describes, if it's a valid machine, or it's going to give us this always rejecting machine otherwise. So how exactly are we going to be able to define this fancy m function? Well, when we look at a Turing machine and look at all of the attributes, all the components of a Turing machine that we need in order to define it, we essentially have like a set of states, we have an alphabet, and we have our transitions. And all of these components we see in a Turing machine are actually finite. So to describe a Turing machine, we basically need to say, here are the states, here are the arrows among the states. And when we look at these arrows among the states, well, that's just a function, where the inputs to this function, we said, were going to be the current state of the Turing machine and the current character being read from the tape. And then the output was going to be the next state in the Turing machine, what was going to be written to the current location in the tape, and then also what direction to move the tape, or how to move the tape, whether that was left or right, or stay in the same place, or actually halt the machine. So for the state, for the alphabet, and for the directions of the machine, all of those are going to be finite sets. There are only finitely many options, meaning that the transition function of this Turing machine must itself be a finite function. And we know that all finite functions can be represented by NAND circuits. And we also know how to represent NAND circuits as sequences of bits. So we definitely know that any Turing machine we can represent as a string because we know how to represent its transition function as a string. So we can just represent a Turing machine by representing its transition function as a string in the same way we talked about doing for NAND circuits. Okay, so now that we know that we can represent machines with strings, and then we can get the machine associated with some string using this fancy M function, we're going to talk about another fancy function, this fancy L function. So this fancy L function, what it does is it receives as input a machine. So it's going to receive, let's say, some machine M as input, and it's going to return a language as a result. So this fancy L function maps machines to languages. And we say L of M, fancy L of M, is the language of that Turing machine M, where the strings that belong to fancy L of M are all of the strings upon which that machine will accept, will return 1. So what we're going to be talking about, we're restricting ourselves today to specifically these accept reject machines. Hopefully, you know from last week some of the relationship between a couple of the Turing machine models that we've mentioned so far. We're sticking to just accept reject machines this week. So L of M, fancy L of M, refers to all of the strings which Turing machine M will accept, will return 1 on, and that is the language of the machine. So now with these two things, we have everything we need to define this self-rejecting language. The idea behind this self-rejecting language is it's going to contain the set of all strings that, when you consider them as a representation of a Turing machine, would reject themselves as input. So, to define this formally, self-reject is going to be the set of all strings W, such that W does not belong to the language of the machine which W represents. So W does not belong, the set of all strings W, so where W does not belong to the language of the machine which W represents. So in other words, if we were to take this machine W, or if we were to take this string W, and then determine which machine W represented, and then run W on that machine, we want to know whether or not that would end up returning a 0 or a 1. If it returned a 0, then W belongs to the self-reject language. If it returned a 1, then W does not belong to the self-reject language. So the definition of self-reject says that W is going to belong to the language self-reject, provided that if I were to take the machine which W represents, so what I want to do is I want to apply the fancy M to W, so now that gives me the machine which W represents. And what I'm going to do is I'm going to say, take the machine which W represents and apply that to the string W. So if that equals 0, then that means W belongs to self-reject. And if it equals 1, then that means W does not belong to self-reject. So if the answer to applying the machine which W represents to W is equal to 0, then that means that W rejected itself. So it belongs to this self-reject. Otherwise, if this was equal to 1, then W did not reject itself. So W does not belong to self-reject. So basically what's going on here, we can consider kind of this table, where each row in this table is going to be one of the potential options for the W. So it's going to be some potential description of a Turing machine, and then each column is going to indicate whether or not that Turing machine was going to accept when given that string as input. So for instance, maybe we have the empty string is going to represent some Turing machine. So is when we apply fancy M to the empty string, is that going to accept or reject the empty string, or 0, or 1, or 0, 0, and so forth. So each of these rows is a potential W, and each of the columns says, if I find the Turing machine represented by that row, then is it going to accept or reject that particular string? Now, this isn't the actual table, because most of these strings labeling each row are not going to be valid Turing machines. We need to have, it's probably going to take several bits in order to represent any particular Turing machine. So this is just meant for an illustration. This is not the actual table, because the actual table would require way more space than I'm able to provide in just one image here. But what we can do is we can find the identity of the self-reject language using this table. So the definition of this self-reject language is essentially we're saying self-reject of W. So if we want to figure out what is the answer for self-reject of W, that's going to be, well, I'm going to take the machine which W represents. So this is fancy M on W, find the machine it represents, and then apply that to W. And then whatever answer I get from there, I'm going to do the opposite of that. So it's going to be not the opposite of the result of applying the machine W represents to W. That is the definition of self-reject. So now when we look at this table, we can find which W's belong to self-reject by essentially looking along the diagonal of this table. So when we look along that diagonal, that tells us whether or not the machine W represents accepted the same string W. So for everywhere on this diagonal where we saw a 0, that meant that string W was going to belong to this self-reject language. Okay, so now we have defined this self-reject language. So now let's demonstrate that this self-reject language is not computable. So in order to do this, we're actually going to do a proof by contradiction. So we're going to say assume for sake of reaching a contradiction. So assume for sake of reaching a contradiction, that some Turing machine computes self-reject. So assume we have some Turing machine that computes self-reject, and we're going to say let W sub SR represent such a Turing machine. So we've said, let's assume towards reaching a contradiction that we have a Turing machine that computes self-reject, and we're going to say the string WSR is going to be a string which represents that Turing machine. In other words, fancy M applied to WSR is going to give us some Turing machine that computes this self-reject function for us. So now let's consider, does this string WSR belong to self-reject? So self-reject is a language, so it's a set of strings. WSR is a string, so either it's going to belong to self-reject or it's not. Let's try to figure out what the answer should be. There are two options. So option 1 is going to be that WSR does belong to self-reject. And then option 2 is that WSR does not belong to self-reject. So let's consider each of these in turn. So option 1, we're going to say that W does belong to self-reject. So if W does belong to self-reject, well, the definition of self-reject was the set of all strings that reject their own, that when considered as a Turing machine, reject themselves as input. So if W belongs to self-reject, then that means WSR does not belong to the fancy L, so the language of the fancy M, the Turing machine, which WSR represents. So if W belongs to self-reject, then that means W does not belong to the language of the machine which WSR represents. But we defined WSR to represent the machine. So this was itself self-reject. That's why we chose WSR, because the language of the machine WSR represented, we said was exactly self-reject. So option 1 says that if WSR does belong to selfreject, then that means WSR doesn't belong to selfreject. So that is a contradiction. So let's look at option 2. All hope is not lost for this theorem yet if option 2 works out, so let's try it. So if WSR does not belong to selfreject, that must mean that WSR does belong to the fancy L, the language, of the fancy M, the machine, which WSR represents. So, because of the definition of selfreject, if W does not belong to selfreject, it must have been that WSR did belong to the language of the machine WSR represented. But, once again, we saw that that language was itself selfreject. So if WSR does not belong to selfreject, then WSR must belong to selfreject, which is another contradiction. So we know that this question cannot be answered. So if this question cannot be answered as long as there was a Turing machine that could represent WSR. So the only way to sort of resolve this issue of we can't say that WSR belongs to selfreject and we can't say that WSR does not belong to selfreject is we have to assume this string WSR does not exist. So we must conclude that there is no string that represents a Turing machine that computes selfreject. So therefore, no Turing machine computes selfreject. So now we have a first function that we know is not computable. Now, this is not necessarily a useful function. It does not seem like we would ever care about what Turing machines reject themselves, except for the purpose of some sort of proof like this, some sort of abstract proof like this. But now that we have one, we can start to sort of navigate the space of what's going to be computable and not computable. And this is actually going to come in handy for us to identify other functions that are not computable. And those are going to be functions that we might care more about.